variety of ways of making amides, and they're on the bottom of our ladder of reactivity. So one thing we can think about is essentially converting each of the species that we've already talked about into an amide. And I'm not going to rewrite all of the mechanisms here. It's all based on things that we've already seen. So we could take this acyl chloride and react this with an amine, as we've done before, and we'll make the amide. So we could take an anhydride, have the amine attack, and turn this into an amide. We could take, like what we just did a few minutes ago, an ester, and react this to form an amide, or a thioester. This doesn't work with the carboxylic acid itself, and it's the same idea that we saw with our other potential nucleophiles that can also act as a base, and by it I mean the amine. And so if we wanted to make an amide from a carboxylic acid, that's not going to work, because we're just going to end up with this acid-base reaction. So if you had a carboxylic acid and you really wanted to turn this into an amide, what you'd want to do is first convert this carboxylic acid into some other derivative. Any of these up here would work. Acyl chloride would be a good one. React it with thionyl chloride, SOCl2, make the acyl chloride, and then in a second step, react it with the amine. Now, these amides, being at the bottom of that ladder of reactivity, are really quite stable, but they can be hydrolyzed. Now, to take a reaction with the amide, so now we're starting with the amide, it can be hydrolyzed to form either the carboxylate on the top here, or the carboxylic acid under either basic or acidic conditions. And notice that's what's the difference here. So we can take the amide, can treat it with sodium hydroxide and water, and because of the stability of the amide, this requires heat. So we're going to heat this up to form this species. And since it's under basic conditions, it's the deprotonated form. As well as we can heat this amide up in the presence of acid and water, and we'll end up forming the carboxylic acid. So it is possible to hydrolyze it. Sorry, I saw a note about going up. Let me make this smaller so we can see this. Due to the stability of these amides, requires the heat, so much more vigorous conditions. So a variety of ways to review here, a variety of ways to make the carboxylic acid, a variety of ways to make the amide, and these different carboxylic acid derivatives, an acyl chloride, an anhydride, or an ester. I'm pausing to write it down. Some of these things I had written out what I posted, so that we don't have to rewrite everything. I'm going to slowly scroll up. So as we're also writing this down, it's interesting to note how the amide being quite stable, right? If we have some other R group over here, this will have in the biochemistry world is the peptide bond. And so the peptide bonds are really quite stable. However, we do have to degrade peptides, and so in things where enzymatically, enzymes like the proteases, chymotrypsin and trypsin and things like that will be the enzymes involved in breaking down these peptide bonds. And they operate under acidic conditions too, in the stomach. Okay, is it all right if I go up now? I'll keep going. Let's see, make this maybe that size so we can almost see both of them here. So I wrote this out ahead of time because we've already seen things like this, similar to previous mechanisms. So on the top here, we're going to take our amide, again, and we're going to hydrolyze it to a carboxylic acid or carboxylate under basic conditions, the top route here on the higher page, or under acidic conditions. So in terms of the mechanisms, we have our amide, we have our hydroxide, it's going to act as a nucleophile, attacking the carbonyl group, end up with this tetrahedral intermediate here, which is then going to eventually kick this group out. Now, one thing that I've shown here that is also a bit of a detail, but again, an important thing is this is overall would be it's a bad leaving group. It's worse than the methoxide. It has a much higher pK of ammonia. So this would end up leaving as NH2 minus, which is going to be quite energetically unfavorable. So what actually probably happens is that in the presence of water here, that as we're reforming the carbonyl group here, which we're going to have in our product, this is not actually leaving solely as NH2, but it's actually picking up a proton off of water. It's basically at the same time. So that we're avoiding formation of NH2 minus and then forming ammonia here, NH3. So that's what I've drawn here, whereas this arrow to the carbon-nitrogen bond, so we're protonating it, the leaving group at the same time as it's leaving. And then because this carboxylic acid is in base, this is under basic conditions, we're going to have an acid-base reaction at the end where the hydroxide is just going to deprotonate this and generate the carboxylate. Again, you might not want this carboxylate. Maybe you want to stop at the carboxylic acid, but just under basic conditions, this is the way it is. You have the base that will deprotonate this. So that's the base reaction. Now, I think we should have the top there, so I'm going to make this a little bit bigger. Just show these two mechanisms. How about under acidic conditions? See if this is similar to what we've seen. So now we have our amide. Under acidic conditions, we're going to first protonate the carbonyl group, making it more electrophilic. Water is going to attack, forming our tetrahedral intermediate that we have here. Now a series of proton transfers. We're going to take a proton off. We're going to put a proton onto our nitrogen to turn that into a good leaving group. Kick out the leaving group, shown here. And then we'll end up with our carboxylic acid. Now we're under acidic conditions, since we had H3O plus here, generic acid, so the carboxylic acid will stay protonated. And actually, because we have acid around, this ammonia here will also get protonated. And that's what I scribbled down below here, is that NH3 will also get protonated. So this is going to form ammonium and water. And there'll be some counter ion to that. So those are our hydrolysis reactions, hopefully very similar to what we've seen, say, with the esters. We're going through this a little quickly, so I'm just going to slowly scroll up. Hopefully that's all right. How about I leave that one there? Okay. So some other reactions. How about if we have a compound that has both an amine and, say, an ester on it, and then it looks like this is going to end up forming this species here, which is a cyclic amide, and that's known as a lactam, Lactam. So cyclic ester, the oxygen here is a lactone. Cyclic ester is a lactam. There's probably really nothing new in this reaction compared to what we've already seen, is that we could have our internal amine attack here, and we'll form a tetrahedral intermediate, and then we'll end up kicking out, I won't redraw the whole thing if that's okay, we'll kick this group out, and we'll end up just cyclizing, just like we saw with our lactone. Then another one is, how about reduction? So we've been carrying out these reduction reactions with lithium aluminum hydride. Here now it looks like we can take this amide, and we're reducing it all the way down to the amine. Notice we have a primary amine. So let's see what is happening in this particular reaction. So let's take our starting amide, and we'll just abbreviate this as H minus. And now we might have something like this. And now the thing is, with this sort of a reaction here, we have some really we have a really bad leaving group here that is a potential of the NH2 to leave. So instead, what we're probably going to have to do is to get rid of this oxygen that we have here. And this is going to occur through a little bit of a different mechanism than what we have seen. But I just want to highlight it up to this point in that we have this bad leaving group here. So this NH2 normally is not going to leave even under these conditions, like with this excess lithium aluminum hydride. So we'll have some parallels to the mechanisms that we've seen, but there are also some differences here. And so in this particular case, we're going to end up with this amine. But I think in the interest of time, I didn't want to go into this one in much more detail so that we have some time to talk about the nitriles. So we're skipping kind of quickly through the amides, but I just wanted to know, I'm going to make this a little bit smaller here, that a lot of the chemistry that we're seeing with the amides overall parallels a lot of the things that we have seen already.